In this video, I'll show a complete stepper motor control project using an STM32 board, DM542 microstep driver, and a NEMA 17 stepper motor. The final result is this. From a simple desktop GUI, I can enter the number of pulses, choose the direction, set the speed in RPM, and send the command directly to the STM32. The STM32 receives the command over UART, generates step and dur signals, and the DM driver moves the motor. So the complete chain is PC, UART, STM32, DM driver and stepper motor. Here I'm sending movement commands from the PC. The field pulses controls how far the motor rotates. The field direction controls clockwise or counterclockwise rotation. The field speed, RPM, controls how fast the motor moves. When I click Send Move, the GUI sends a text command through the USB serial connection. For example, internally it sends something like move 1600 CCW 180. This means move 1600 pulses in counterclockwise direction and 180 RPM. The STM32 parses this command, calculates the timer frequency, starts the PWM output, counts the generated pulses, and stops the motor after the target number of pulses. A stepper motor is not controlled like a normal DC motor. We do not just apply voltage and let it spin freely. Instead, the driver receives digital step pulses. One pulse means one step or one microstep. So if the driver is configured for 800 pulses per revolution, then 800 pulses one full revolution, 400 pulses half revolution, and 200 pulses 19 degrees. This is why the pulse count in the GUI controls the final angle of the motor. The STM32 does not need to know the mechanical position from a sensor in this simple setup. It assumes that every pulse is correctly executed by the motor. This is called open loop control. Now I can change the speed. The important point is that speed is controlled by the frequency of the step signal. If the STM32 sends pulses slowly, the motor rotates slowly. If it sends pulses faster, the motor rotates faster. For example, if the driver is set to 800 pulses per revolution and we want 120 RPM, the required frequency is. So the STM32 timer must generate 1600 step pulses per second. The direction is simpler. The STM32 sets the DIR pin either high or low before starting the movement. To make the movement visible on camera, I added a 3D printed disc and arrow to the motor shaft. Without this, the shaft is small and it is difficult to clearly see rotation, direction and angle. The printed part makes the demonstration much better, because now we can visually see the motor position. This is especially useful when testing commands like 19 degrees, 180 degrees or one full revolution. At this point, the full system is working. On the left side we have the DM542 stepper driver. At the top we have the STM32 NUCLEO board. The motor is connected to the driver outputs. The PC communicates with the STM32 through the ST-Link virtual COM port. The STM32 is not powering the motor, it only sends logic signals. The motor power comes from an external DC power supply connected to the DM542. So the STM32 is the brain. The DM542 is the power stage, and the motor is the mechanical output. Before building the final demo, I designed a small mechanical indicator in FreeCAD. The idea was very simple: create a disc and an arrow that can be mounted onto the stepper motor shaft. After modeling the part, I exported it, opened it in a slicer, prepared it for printing, and printed it on a 3D printer. This is a good example of how embedded systems, electronics, mechanical design and 3D printing can work together in one project. Even a simple printed part can make testing and demonstration much clearer. Now let's look at the control principle. The STM32 sends a square wave signal to the step input of the driver. Each rising edge of this signal is interpreted as one step command. The driver then energizes the motor coils in the correct sequence. The duty cycle of the signal is not what controls the speed. The speed is controlled by the frequency. So in this project, step frequency, motor speed, number of step pulses, motor angle, DIR, signal, rotation direction. This is the core idea behind stepper motor control. Inside the stepper motor there is a rotor and a stator. The rotor is the part that rotates. Usually it contains permanent magnets. The stator is the fixed part around the rotor. It contains electromagnetic coils. When the driver energizes different coils in sequences, the magnetic field changes position. The rotor follows this change in magnetic field step by step. A common NEMA 17 stepper motor has a step angle of 1.8 degrees. That means 360 degrees divided by 1.8 degrees equals 200 full steps per revolution. The driver can also use microstepping, which divides each full step into smaller electrical positions. This makes movement smoother and increases the number of required pulses per revolution. Now let's connect this idea to the real wiring. The DM driver has motor outputs A+, A-, B+, and B-. This is called to the two motor coils. The power supply is connected to V+ and to V-. The STM32 is connected to the control inputs, pulses plus, pulses minus, direction plus and direction minus. One important safety rule: never connect or disconnect the motor wires while the driver is powered. The motor coils are inductors, and disconnecting them under power can generate voltage spikes that may damage the driver. The DM driver has deep switches on the side. Some switches configure the motor current, other switches configure the microstepping mode, or pulses per revolution. The current table is used to match the driver output current to the motor current rating. The pulse per revolution table defines how many step pulses are needed for one full revolution. For example, with a 1.8 degree motor, 200 pulses full step, 400 pulses half step, and so on. The driver assumes a standard stepper motor. It does not automatically know the motor angle. We configure the driver with the deep switches, and then we configure the same pulses per revolution value in the firmware. On the STM32 side, the firmware reads incoming UART data character by character. The function collects characters into a buffer until it receives a new line character. When a full line is received, the firmware parses the command. So the raw serial text move 1600 CW70 is converted into internal values, pulses, direction, and speed. Then the firmware calls the motor control code. This is much better than using block and scan, because the firmware does not stop forever waiting for input. It can continue checking patterns, handling the motor, and processing other tasks. The motor control logic is placed inside C++ class. A class stores the timer, the PWM channel, the direction pin, the pulses per revolution value, and the current movement state. And the command arrives, the firmware sets the speed. The speed in RPM is converted into a step frequency. Then the timer auto reload value is changed to generate this frequency. The timer output produces the step signal. The PWM interrupt callback is used to count how many pulses have been generated. When the counter reaches the target pulse count, the firmware stops the PWM. So the motor moves exactly the requested number of pulses. One important lesson from this project is that hardware timers are necessary for accurate motor control. At first, It is tempting to create pulses manually using delays, but this is not precise enough. Using the STM32 timer gives stable frequency, accurate pulse generation, and better control. Another important lesson is initialization order. In embedded C++, we must be careful with global objects. The timer and peripherals must be initialized by cubemx generated code before we configure them in our own classes. So in this project we built a complete stepper motor control system. We used STM32 NUCLEO, DM542 stepper driver, NEMA 17 stepper motor, external power supply, UART communication, Python Tkinter GUI, STM32 timer, PWM, C++ firmware structure. The project now supports pulse count, direction and speed control from the PC. Possible improvements are acceleration and deceleration ramps, non-blocking UART with interrupts or DMI, a display connected directly to the STM32 potentiometer, speed control buttons for preset angles, and eventually G-code style motion commands. This project is a strong foundation for understanding how real 3D printers, CNC machines and automation systems control stepper motors.